Can you hear me up there? Can you hear me? Okay, good. Hello, everyone. Thanks for coming this evening to our third town hall. We have a few presentations that we want to share with you. We have been working a lot on the different studies that we have talked last time. We continue doing those studies, so this time we're going to share a little bit more information on what we have found and the projects as we move forward. Where's that? Yeah, pointer. Right here. Okay, let me introduce the team that today is going to be talking. Myself, I'm Fernando Rodriguez. I'm the director for the project, for the mine. I've been with Albemarle about 6 months. So the rest of the team today will be Ron Lindsay, safety manager. He'll be talking about safety share. Safety is very important for us, as we have talked about last time. Joy Dean is our group hydrologist. He will be talking about all the studies that we're doing in terms of water. Henry Walkie is our group metallurgist. He's going to have an overview of the concentrator facility. He's going to talk about the processes that we're looking at to do with the processing of the ore. Like I said, we have also the safety share. We're going to be talking about briefly about the DOE Energy, Department of Energy award. We're also going to have some the water studies and the concentrator. At the end, we're going to have some Q&A, so please feel free to ask questions while we're talking here and during the presentation, but also at the end of the presentation, we will have a general Q&A. Okay, with that said, we're going to get Ron Lindsay. He is going to talk about a safety share, which is our core values, how we protect our people, and how do we make sure that we work safely in every area that we work. Go ahead.
Hello, everybody. Thanks, Fernando. As Fernando said, I'm Ron Lindsay. I'm the safety manager. Like Fernando said, one of our core values is safety, and so just going to give you a quick safety share. We start every meeting with the safety share, just something real quick, but it's very informative. First thing I want to talk about, though, is if something happens here and we have to get out, we can come in the way you came in, but if we can't get out that way, we got 2 exits on each side, so you can exit out that way as well. So that's how we go if there's an emergency. Hopefully there won't be one tonight. What I want to talk to you about is ergonomics. Ergonomics is a big deal. They say there's about 2 million back injuries a year, but only 15% of them are due to like falling or say a car wreck. So 85% of them usually happen at home, and it's due to this kind of stuff here, improper lifting, twisting, turning, that stuff. Our body's designed to stand upright like this. Okay, so that's why it's important. We've always been taught to lift with our legs and keep our back straight, because you can see there in that picture right here, it's 10 pounds and I have my back straight. That's how much force is on my spine. But our spine is also like a lever, so when I bend over and go to pick it up, it puts 100 pounds of force on my lower back, because it's like a fulcrum of a lever. Then it says the average, I don't know where they get these, they says the average torso weighs 105 pounds. Mine's a lot more than average. But so that you put another 105 pounds of force on there as well, and it actually adds up to 1,150 pounds of force on your back if you're not lifting with your back straight. So that's very important to do that. This is another good picture that we like to show. Just like when we're carrying stuff at home, at work, wherever, just keep it close into your body. You can see there, it just shows you got a green zone, yellow zone, and a red zone. And we've all packed stuff. You know, the closer to your body, the easier it is. You hold it clear out here, it's hard to carry for very long. And you can see here the proper way to lift. What I tell people at work and stuff is if you have little kids at home or grandkids at home, set something on the ground, ask them to pick it up, and they automatically do it this way. And then they grow up watching us do it the wrong way, and then they start doing it like that. So just be mindful of that. This is a big one. This is a new thing that's coming about, and you may have heard this. It's called texting neck syndrome. This is another thing that blows me away too. So my torso is overweight, but my head's smaller and I don't got no hair. And they say the average head weighs about 10 to 12 pounds. So when I'm just standing up here with my head straight, at 0 degrees, there's 12 pounds of pressure on my spine. But when I'm looking at my phone all day like this, at 60 degrees, it increases it to 60 pounds. Okay, so just be mindful of that. And they're starting to see a lot of injuries due to this. But how do we fix that? It's due to this ergonomic injury triangle: force, frequency, and posture. It just depends on the amount of force, how often you're doing it, and the posture that you're in. Younger kids may not affect as much as older people. We just went through Christmas, and I know if you ever sat on the floor and wrapped Christmas papers and got up, it's hard and it hurts, and that's because you're in that, having that force, that frequency, and that awkward posture. So just watch yourself. This ergonomic stuff's a big deal, and that's all I got, and I'll turn it back over to Fernando.
Thank you, Ron. That was a good safety share, especially for, everybody has a cell phone these days, so it's important to understand that. Okay, let me give you a brief update on the Department of Energy award that we have. As it was published, Albemarle awarded $150 million from grant from the U.S. Department of Energy. And this is basically to support the development of a lithium concentrator at King Mountain here in our community. It was funded by the Bipartisan Infrastructure Law to expand domestic manufacturing of batteries and the electrical grid, and to expand access to the materials and components that currently are imported from other countries. So we just want to make sure that we have our own supply of lithium in the country. Additionally, the grant will support sub-recipients on the education side, which is focused on development of the workforce for the mine. And details is $5 million for Cleveland Community College for the training of students to become specialized in the mining and in different disciplines that are related to the work that we're going to be doing. $1.5 million to NC State Mineral Research Labs, and also $1.5 million to Virginia Tech for mineral research as well. So this is basically what the $150 million grant are going to be used for. Now let's get into last time we talked here. There were a lot of questions about hydrology, about water, about how things move around the mine sites, and specifically that are related to the community. So here's Joey Dean, our hydrologist. He's going to walk through some of the studies that we're doing.
Okay, so my name is Joey Dean. I'm the hydrologist that is at Kings Mountain, and I'm happy to be here. So thanks for coming, everybody. So in 2022, we did a lot of work to expand the groundwater monitoring network and really get all of our baseline data down for the groundwater, and really just kind of try to understand the system and characterize, what it's like on site and in the areas around site, around the pit. First thing we had to do was determine, what else is interacting with groundwater around the site. And so we had AECOM, which is a big engineering firm. They came in and did a really exhaustive water well survey for private water wells. And they used as much public record as they could. They did things like use Google Earth as well and zoomed in on places where they suspected wells, and you could see wells in yards. They drove around town and looked for places where you have the rock that covers your well and things like that, just to determine where there's a well that's suspected or an actual well present. Something that's interesting is in the North Carolina database for public water wells only goes back to 2007. So, there's obviously people in town that have wells that are older than that. And so they really, really went around and did a really good job on this audit and determined, you can see the map there, that within a 2-mile radius, there's a lot of water well users and suspected water well users. So we, used that information to kind of, build where we wanted to have the baseline groundwater monitoring network installed. That's the pointer. Sweet. Okay, so why do you need a groundwater monitoring network? And so my presentation today is going to be a bit of learning for all of us for some groundwater jargon and some of the things that I have to think about on a regular basis. And so if I talk to people, so people's eyes don't glaze over and look at me crazy, you know, I'll give you a couple definitions here. So when we drill a bunch of holes and we install wells, you know, we're obviously collecting water quality data and water level data. But from those wells being drilled, we test them as well. We want to determine what's actually governing the flow of groundwater, okay? And so we do what's called aquifer testing. And that's really done to determine, you know, what are those physical parameters in the ground that are allowing groundwater to go from one place to the next to migrate. So the term that is the number one physical coefficient, I guess, that we try to determine that's useful in just about every piece that you do when talking about groundwater, you know, modeling or movement or any kind of, you know, determining what's happening with groundwater is hydraulic conductivity. And that's really the parameter we use just to, that groundwater physical parameter is what tells you whether or not, you know, groundwater can flow easily through a media and what kind of storage, helps you understand what storage is like. So it's always based on, you know, the pore spaces, if it's sandy or silty material. In our case here, we're sitting pretty much right on top of bedrock. So it's obviously based on the orientation of the fractures and the spacing of those fractures. We did 3 types of aquifer tests, pump tests and packer tests and slug tests. This figure here, I hope you guys can see it good. It's a gigantic screen, but I'm glad it's so big because it's a really, really important figure for the area. If you ever kind of wonder what it looks like underground in a really conceptual manner based on groundwater flow, obviously if this was detailed geology, you'd have different things going on in here that as a hydrogeologist, I'm not super concerned with. I really want to know if water can flow through it. You know, like Josh is going, oh, those rocks this, and Jen's over there going, this rock's this, and I'm like, does water flow through it? I don't care, you know. So, but you can see that based on this conceptual geology here, and this figure is taken from the Indian Creek study done by the United States Geological Survey. Indian Creek's right up the road. This is we have the regolith here, which is that red clay that we have, and that's the weathered leftover from the bedrock below it. And you can see where there's fractures a little bit more where it says, you know, there's valley and draws, where there's streams. And water takes the path of least resistance. So if the ground's more broken up in that area, you'd expect that that's where you're going to have your stream channels form. And then at the very bottom of that, we have really impermeable basement rock. So I feel like this picture, if you can remember, you know, one thing about wondering, if you're ever wondering what's going on, you know, what your well might look like down, and this is pretty much what you're going into. And you can see this is a weird unit, divide in miles, so they do these in you know, tenths of a mile. So most people's water wells are sitting right in this area here. Okay, so pumping tests. The pumping test, obviously, you have a well, you put a pump in it, and you run the well, and you're determining from where the water level was down to what it draws down to while pumping, and you monitor that information over time. You're taking water level measurements and recording flow at that same time unit, and you're going to calculate from that what the hydraulic conductivity is in your well. Awesome thing about a pump test, this is like the Cadillac of groundwater testing, is an aquifer test. Let me just finish the slide real quick.
Joe, can you pick up that mic and speak into it, please?
Yeah. Oh, you want me to carry it? Okay. All right. So, yeah. As I said, we pump the well, and when you pump it, the water level draws down. You record flow. You record the water level drawdown as you're pumping. And then you calculate hydraulic conductivity in the well. But the nice thing about a pumping test is if you have the opportunity to have an observation well nearby, you monitor the water level change in that as well, and from that information you can determine what the groundwater parameters are for flow between those two wells. So this is like I said, this is the Cadillac of doing testing for groundwater. This gives you the most information in two directions. So we did a lot of these. We also did what's called packer testing. Packer testing is when you have this apparatus that you put down the borehole while drilling. And it has on either end a lower packer and upper packer. And what that is that's a bladder that you fill with compressed air. And it just presses itself out into the borehole and wedges itself in there. And then in between those two sections is an open area that you push water down the hole, you inject water down the hole, and you're testing this interval in the borehole. And so you do a specified volume, and you measure the pressure as you're having water go down the hole. You're injecting that water, and you watch the pressure. And as that pressure changes and it does a certain thing, you can calculate what the hydraulic conductivity is in that interval you're testing. What this one is specifically done for mostly is determine what the fracturing looks like as you get deeper in the ground. So tunneling operations, underground mining, open pit mining, excavations for highways, things like that, all end up doing this kind of test. It's a very big geotechnical, it's more of a geotechnical test to determine ground strength and things like that. But it lets you know as you get deeper what kind of parameters, what kind of situations you might run into for groundwater flow as well. Something to make clear whenever you talk to someone about packer testing, though, is that this is not fracking. So you may be injecting water and you may be monitoring a certain pressure, but fracking is a completely different operation that the oil and gas industry uses. When you frack, just real quick, you fracture the ground oftentimes using explosives or pressures that are up in the tens of thousands of PSI. We're talking about measuring like 100 PSI max type stuff. And then the other thing is when they fracture those holes down in the ground for oil and gas, they're putting chemicals and like silica sand down there to keep the holes open, so that they can extract the fluids they're looking for. So we don't do anything like that when you do packer testing. Slug testing is the last thing we did. Slug testing is something you do often when you have wells that do not have high flow. So you drill the well, you install the well casing, the gravel pack, you construct it to the state standard for a well, a monitoring well, or a pumping well. And after you do that, you develop the well. That's when you remove water and you flush it to get all the cuttings of the drilling out, all the little ground up pieces of rock that fill up fractures and fill up pore spaces. So you get all that stuff out of there. And then you decide what kind of test you're going to do, and that's based on how quickly that water comes back. And if it takes a long time to recover back to the water level it was at when you first finished the hole for drilling, you end up thinking, well, if it's didn't come back for a long time, we should do packer testing, because a packer test is meant to remove volume from the water column, but it's a volume you put in there. So this says well slug, right? So in this case, this would be like a molded plastic tube tied to a string on the end, or a piece of cable. And you slide that down into the well, you get it below the water level, and you're monitoring it with this data logger that's down there. So you can see when the water level recovers back, so it gets used to having that volume in the water column. You usually only make the thing like as long as your arm, because you need to have a nice smooth pull of it. You don't want it to bounce. So it's funny watching people do it, because they're trying to go up on their toes and make sure they got the thing all the way out of the ground, out of the water. But it's the same as doing a pumping test, because you're removing a known volume from the water column, same as you would do with pumping, and you monitor that head change, the water level change, and from that you also can calculate hydraulic conductivity. The only downside to this is you're really only getting that hydraulic conductivity at that well. So if you have to do a lot of slug tests, you hope that you have them all over the place, so you can kind of get a spatial awareness of what hydraulic conductivity is. So again, back to that question, why a groundwater monitoring network? We need that baseline data. We need to know what we have now so that we can learn about it and then tell if there's something that changes and either investigate or use those inputs to build the groundwater model that we have to have as well, because you need to be informed, you need to be able to predict out in the future what might happen in different scenarios. That information all goes into the groundwater model to calibrate it. So we have the pre-mining inflow estimates from records, we have the pit lake recovery that we were able to reconstruct, the groundwater level hydrographs of drilling in 2018 all the way up until last year and then on into this year. And we got these two gauge stations. They're gauge stations for the flow in those two watersheds. And what you do when you're calibrated is you're trying to get that model to reproduce that data, trying to tell you that, okay, that's the same as on that date, that's what the water level was in that place. And the reason you want this groundwater model is to inform flow rates during operation. What will the pit lake recover to after a certain amount of time? What causes that recovery? You also get to get an idea of any possible development of the drawdown cone. And when I say drawdown cone, I mean, is there a cone of influence in a depression in the groundwater that occurs due to due to pumping the water out of the pit? And then, is there going to be the levels in nearby wells? Are we going to impact the wells, and are we going to impact the base flow in these watersheds that we are connected to? And so I'm going to go over some of the empirical data that we found, because the model is great and it's good for determining the future from information that you have recorded that you can actually go out and measure in real life. So the nice thing about being able to go out and measure things in real life is you can actually characterize things and get an idea of what you have in nature. So this is the Packer test data, and you remember the Packer test data was what we used to determine how fractured the ground is as you get deeper. And this graph, shows that water flow as you get deeper, the fractures that water flows through at depth, this is getting deeper as you go down. And then to the right here, is like the best hydraulic conductivity that we could have on site. And so what you see here is this upper trend to the right. Pretty much everything above 400 feet has a hydraulic conductivity that gets down to 10 to the negative 3 feet per day or better, which is 10 to the negative 3 feet per day is not exactly fast movement for water. 10 to the negative 1, you see that's 1 feet per day, right? So that would be ideal. That have it pretty slow, and you can see that it trends down to as you go deeper, it's more and more tight. And that's a good thing, because as we excavate the pit, we need to know that we're going to have, as we dig, we're going to have really good structural strength in the rock. We need to make sure it's a safe working environment. And we also need to know that we're not going to have pit inflows coming in that may impact things that we didn't find during our base flow study and baseline studies. So the likelihood of that happening after seeing this data is it's very unlikely. And this is just the different rock types that we did these tests in. So characterizing the hydrology of the site, we determined obviously from the topography. So this is going north to south to Kings Creek. The pit has a water level that's below the rest of the land around it. So water doesn't flow from the pit to Kings Creek, not naturally. That will happen by pumping. And then this is the same type of graph, except going east to west. So we have west over here going east to the Martin Marietta property and to the east, where the Martin Marietta property is between us and there. And you can see that the pit is lower than than any of the topography around it. So there's no groundwater that goes from the pit out. It's sitting in a bowl. And from the previous graph, we know that bowl is pretty tight. It's like a bowl of cement. And then, in my opinion, this is my favorite one. This is the most poignant. Well, we have the west, north, and east side of the pit. And we had migration possibility to the south. And so water flow really is in this direction. You have this thing called preferential flow. Water is going to take the path of least resistance. So it wants to head this direction if it does flow at all. These values here, something to remember with groundwater flow is it's not fast. Unless you have cave formations, you really don't have water that's going to move within feet even in a year. It's very, very slow. Yeah, so this is 85. And 161 comes up right here. And so this is the same image except with the geology. We've determined changes are. This is the Martin Marietta pit here, so there's a rock type there, different rock type here. They're faults and folds where, as this stuff all came together millions of years ago, it ground all up and got crunched up. And so what we have is we have flow that can go parallel to this, but it doesn't go across it very well. You really don't have flow going perpendicular to that across. So that's a good thing as well, that we know that within the vicinity of the open pit, we really only have groundwater even availability in this area here, which the blue is our ore. Okay, so we really only have the ability to see groundwater flow in the area that we plan on working. That's all I have. You guys don't have any other questions? Okay, well, I'm hanging out, so if you got anything that comes up, let me know. Okay.
So you were saying there's a possibility of migration to the south, but can you describe it? I mean, what is the possibility? Because it says 0.3 per day. What would be the situation that would cause migration?
So when I say migration, what that means is it doesn't mean it's going to happen. What it means is like you have rock that has fractures in it that would allow flow in that direction. But the thing is that there's not really much of a groundwater gradient because water wants to go from high to low, right? In the ground too. You pour water on the ground and you see it flow in a certain direction. So oftentimes what you have is you have groundwater that really mimics closely to the topography. And what we have here is, there's not really much relief. Obviously, so the pit is way below it. But we know that the rock is really tight, so there's not really anywhere for groundwater to go. The only thing that would cause migration is if we pump a lot of it. And from the study that we've done and from our testing, there's not really any wells around that are high capacity. They can't really pump a lot of water. So when I say migration, that word really just means the possibility or the ability for water to move. It doesn't mean it's going to. And again, so say in these types of hydraulic conductivity situations, those really low hydraulic conductivity, you pump a well that does 20 gallons per minute or less. And for a house, that's an awesome well, but 20 gallons per minute or less, to draw down something that's, here, and say you're pumping here, I mean, it would be years and years and years. So again, that's something that even as a student of hydrology, it took me a long time to understand that, water in the ground doesn't really move that fast. If you're in Florida and there's underground caves and stuff, that's a different story, but we definitely don't have that situation here. Did I answer your question? Okay. Anybody else? All right, like I said, I'll be around. Thank you.
My name is Henry Walke. As mentioned before, I'm the group metallurgist, and my role here is the design of the processing plant or concentrator. So the way I see it is I'm a grown-up guy that gets to play with rocks and mud. That's that's what I do, and this is where we are right now. So I don't know, I believe we've covered this in one of our other presentations, but in general, this is what the project is about. We start with geology guys finding what rocks are on the ground, what is good, what is bad, and then it goes into the mine guys who figure out the best way to get it out of the ground. Once that plan is put in place, the execution, which is the drill, blast, and loading, is what delivers the ore or the material to be processed to a processing plant, which in our case, which is what we're going to be talking about tonight, which is crushing, which is size reduction, making big rocks into little rocks, and then taking those little rocks, making them into mud, and getting the good out of there. So that's basically, in very simple terms, what we're trying to do. And to do this, we need to talk about ore, which we've talked before, which is a mineral or a material on the ground where there is enough valuable mineral, in our case it's called spodumene, that's where the lithium is, that you can mine, process, and make a profit out of it. If you cannot make a profit because there is either not enough lithium or there isn't lithium on it, in our particular case, then it's either going to be waste or gang. That's what we have. So now to keep Jeff happy, we're gonna go to the cookies. So on my prior job, the owner of the company used to use this analogy when describing what mineral processing is. And it is basically you have a chocolate chip cookie and you have to get the chips out from the dough. And that's what we're trying to do in this particular case. Our chips are going to be spodumene or lithium mineral. If there is not enough of it, the second case, it is waste material. If it is raisins instead of chocolate chips, it's not going to do any good to us. So it's also waste material. And if the chocolate is really covering everything and you cannot separate it from the dough, then really you're not going to be able to process it. So it's, again, waste material. So what does it look like for us in real life? In real life, what we have is that's an image from the pit, from the old operation. And we got it a little easy in the sense that you can tell ore is white and waste is black. That's, in simple terms, that's what we're looking at. And when we look at ore, within that white, you have this mineral, which is spodumene, which is a lithium oxide mineral. Now, you can see these circles. That is actually spodumene, and everything outside it is not, something else. So when you go back to making a plan to remove the ore from the ground, the mining guys are going to try to remove as much white with as little black on it to deliver to the plant. And in the concentrator, what you're going to try to do is get these spodumene minerals out without taking any of the other stuff. So white is good. Within that white, you have this, which actually has a greenish tint. Now, not all of it is the same. The image below is a drill core from a white zone. And in our case, what we have is a combination of cores, or these big grains, and then it also starts migrating, and then you have very little white specks. And the challenge for us is to recover or design a plant that can recover both the coarse material and the fine material at the same time. You can do one or the other, or we need to do both to be as efficient as possible. So minerals processing is you can call it a science or an art, it's subject to debate, that looks at how to recover a valuable mineral out of a waste. And the same, we can keep going with ore and waste coming out of the pit, going to a size reduction, which is what we call fancy comminution. and then you break them. And what you're trying to do is liberate the valuable material from the non-valuable material. And once you've been able to liberate it, you actually have to separate it. So you concentrate, in our case, spodumene, and reject everything else. In Miller's processing 101, I won't tell when I went to school, but basically you have liberation and separation. That is the core of what we're doing. Breaking, making, and then liberating the spodumene out of the gangue or waste material, and then recovering it. And you tailor your operations to get the most out of it. One particular point that I want to make here is that those separation processes are, for the most part, taking advantage of physical properties of the material. We're not trying to change their composition or anything like that. We're taking advantage of particular physical properties of each of them. And here is a very simplified representation of the steps that are taken to process the ore that we're going to get out of the ground. So if I knew how to use the pointer, I wouldn't have to move around. So I'm just going to go and move around. You start with ore coming from the mine, and the first that goes to crushing and screening. And what crushing and screening is you see them every day at Martin Marietta. You crush, make smaller rocks, go through screens to separate in a very specific size. We need to do the same. We need to break them into smaller particles in order to fit the right size particles to the different operations that we're going to be having in sequence. The first such operation is ore sorting. I showed you before how we have black and white material. So basically it's a bed of ore moving through a conveyor, and there is a sensor that looks at it. And when it is black, it puffs air and rejects the waste material. That allows you to reject about 20% of the mass very early, actually 10% of the mass very early in the process. Then you gotta go to slightly smaller size. So this is done at about inch to 2.5 inches. And then you go to this stage of crushing and screening and go to this next step, which happens at about 1/4 inch to 0.8 millimeters, so it's a very small size. So this here is the next step. Here you have two outcomes. You generate a concentrate. About 60% of our production is going to come from this stage, but you also reject a significant portion of waste material here. And then there is an in-between, which we're going to talk later. So the in-between plus whatever is finer than what you can fit here then gets to the next stage. And the reason you go to this stage is to break it even smaller. Now, if you remember that image that was long at the bottom where you had big grains and little grains, they're basically making everything smaller than those little grains here. And then you have to try to clean it up a little bit. In our particular case, once you go through this stage, one of the unintended consequences is that you end up with a small portion that is very, very fine material. And we call those slimes. You have to remove those. And you have to remove anything magnetic that you can. And then once you've done that, you finally get to flotation, which is another operation where you finally make the spodumene concentrate. Now, you make 40% on that stage, 60% there, so about 40% is going to come out of this process. The product from flotation is dilute. It has only 20 to 30% solids. The rest is water. So you got to make sure that you remove as much of the water so that you can reuse it in the process, and that's done through thickening and filtration. So let's see. Okay. So trying to cover a little bit of each step just to try to explain what we do and the properties that we're taking advantage of, or what are we doing. So crushing and screening is pretty simple. We have one stage using this machine called a jaw crusher. And the reason is because it's like your jaw, and you have a fixed plate on one end, and then a movable plate that is applying a force on the rock. That force makes them to go from big to little. And the same principle applies on the other one, only instead of being one plate, it is a mantle that is rotating in a chamber and applying that force. And again, the whole thing on these stages is to make sure that the big rocks go into little rocks. And the reason you have to do sequentially multiple stages is there is a ratio on how big to how little is going to get. You can only get so little with a starting size. And because we have different sizes that we need for every step, we have to do multiple stages of this. And in between, to control the right size for the specific application is what we use screening, which is like a strainer, like your pasta strainer. It's basically just a surface of identical size holes. And this shakes, vibrates. And anything that is smaller than that hole is gonna go through, and that's your fines. And anything that is bigger is gonna keep carrying forward. And depending on what you need, this might be your product, this might need to go back to be broken down again. You just mix and match this to deliver the right size product. Once we have the right size, we use dense media separation. That's where I said before that about 60% of our production is gonna come out. And the way you do that is you have the ore that you mix with water, that's 1/2, and then you have water that you mix with a medium, what is called, it's a ferrosilicon, it's an inert material, where you control the specific gravity very carefully. Now, the best way to that I can explain that or can just relate to this is when you mix water and oil. You mix water and oil, you shake it, and the oil is going to raise to the surface, and the water is going to stay at the bottom. It's something similar. In our case, we're mixing the solids so that we can control the specific gravity. Water has a specific gravity of 1. The ore we're receiving has a range of a specific gravity. We're trying to find those where we can separate what we want from what we don't want. In our case, we do a first pass at 2.65, where anything that floats, meaning that is lighter than 2.65 specific gravity, is going to be rejected. And we know from test work and analysis that the material in that size, lighter than 2.65, is going to have pretty much no lithium on it. So we can reject it at that point. Then whatever sunk, which is heavier, will go and pass again, only instead of using 2.65, we're going to use 2.9. And in this case, in this second pass, what we're looking at is everything that is heavier than 2.95, which is where the lithium is. And in our case, it gives us a clean concentrate by recovering that heavy material. That leaves us with what we call middlings. It's either heavier than 2.65, lighter than 2.9, the in-between. That mixed with anything that was finer than the size that you use for this, needs to go to the next step, which is the grinding step, grinding and separation. And again, the whole purpose of this is just to make the particles smaller so that you can liberate the minerals. In our case, that's a representation of the ball mill. It's basically a tumbling mill. It's a cylinder that is rotating and rotating and rotating. And there is about 40% of the volume is filled with steel balls. And those balls, as they go up and down, they hit the particles and break them and break them and break them. So you feed it from one end, comes out the other one, and then it goes to the and that guy is what is called a Derrick screen, which is another version of the larger screens that are used in the process. Here, these are vibrating, and the reason they look goofy is because you're trying to maximize the space, and you stack them one on top of the other. That's why they look different. And if this stays, will be great. We'll try that. Anyway, they come out, the water and the mineral come out. They go here, again, it's shaking. Anything, in our case, this is 250 microns, which is very, anything that is finer will go forward in the process. Anything that is coarser will go back and be ground until it's the right size. The reason we're using the screens versus the more traditional equipment, which is a hydrocyclone, is because this gives us a more cleaner cut, meaning that It allows us to be more efficient classifying and prevent that guy from making more and more ultrafine material that we have to waste out anyway. Now, once you have that slurry, we go to these two stages. Magnetic separation, which I'll try to see if it works or not, but it's basically trying, when you get out of the mill, we've used grinding media that is steel. Steel is magnetic. Very small shavings of that material carry with the mineral. So we put it through a drum that has a magnet at the bottom, and as it rotates, it captures that magnetic material and allows the rest to go forward. So in this, I don't know if you're going to be able to see, but we put a whole bunch of bolts inside with glass, and you can see if I take this out, they fell off. And then, because there is a magnet, you can start picking them up in the magnet. That's a simple step what we're trying to do in that stage, just getting rid of magnetic material. And then we go to these liming cyclones, and that's my favorite part. You basically, the material you feed here is a slurry, water and solids, at a decent pressure, and the material starts swirling. As it swirls or turns, the big particles tend to go faster and attach to the wall of the cyclone. And then you have the smaller particles going towards the center. This is a cylinder, and then it's a cone. As it goes down into the cone, the space makes that the small particles get squeezed out, and they go in the opposite direction and come out. That's how we get rid of that very fine material that is very hard to process. And then the coarse particles go at the bottom. And this is no different than, I don't know how many of you have or have seen the Dyson vacuum cleaners that have, or the cyclonic vacuum cleaners. It's exactly the same principle. In fact, we've been doing this probably 60, 70 years before Dyson was cleaning houses. So this is pretty well understood technology. And then the final step in the processing end to recover and spodumene, in our case, is flotation. And flotation, what it is we're trying to make particles not like water. And to do that, we use two reagents. And those reagents are, first is a frother. And basically what that does is changes how the surface tension of the water works. So if I probably should have a glass, but if you put your finger in a glass of water and gently squeeze, eventually your finger is going to go through the surface into the water, right? If there is a force required to break that surface. So what the frother does, which in our case is an alcohol, it makes that surface a little tougher, so that more force for your finger to go through. In our case, which is not different than you taking dish soap and making bubbles, or going out on the street and making, that's basically what the frother does, makes bubbles. And then we also use a collector. Specific to spodumene is a tall oil fatty acid, which is a byproduct from trees. It gets extracted from trees. It's an oil from trees. And what it does is it seeks spodumene, for lack of better words. And spodumene is not just lithium. It has a number of elements associated with it. One of them is aluminum. So the fatty acid, this collector, goes and likes that aluminum site and goes and attaches to it. And it leaves a little tail hanging. That tail doesn't like water. So what is going to happen is that tail is going to poke into the bubble. And then the bubble is going to carry, because where air is and there's no water, and eventually reject. That's how you remove the spodumene or collect the spodumene. Now, it's a little more tricky than just that. You also have to control at what pH you're going to operate. In our case, for spodumene, it's a pH of 8, and we regulate that pH by using soda ash. And the reason for that is that is the most efficient range or point where that recovery happens. You higher, then other things are getting picked up. You go lower, and you don't pick up as much. So it's just a balance, and you're just always tuning and getting that to the right place. But there's no chemical change. Everything up to this point is just taking advantage of a physical property. And once you have that concentrate, the last step is to make it into a form that you can ship it. I've mentioned before that this is usually in the 20-30% solids, meaning there's 20% solid and 80% water. You go into a big settling tank, and you've seen those in sewage plants is one example that I probably shouldn't be using, but that's very typical there. And you add what we call it's a flocculant. And a flocculant is, call it like a glue-like material. It's a long chain that has arms, and the solids attached to those arms. And the more and more solids they attach, the more that flock weighs and the faster it settles. And that allows to separate the solids at the bottom from the water on top. And you come in at, say, 25% solids, and you're coming out at about 50 to 60% solids. And the very last step is feeding that into a filter press, which basically just squeezes the water out. And at that point, we can happily ship, hopefully, our concentrate in a couple of years, sometime from the future. And the other thing that we're doing here is we're not only thickening and filtering our concentrate, we're also all our waste streams, or our tail streams, are also getting filtered and stored on site. And the main reason for that is to use the least possible amount of water in the process in the most efficient form possible. So that's about the extent of it. And I think that was the last for me. Yeah.
Great, thanks very much, Henry. And now we have concluded our presentations. I think we have seen very interesting studies that we are doing on the water part of the hydrology and also the concentrator, how the ore is going to be processed to become our final concentrate of lithium. So now let's get some questions, Q&A. I will ask if you have a question, please you can come up here front. We have the microphone so everybody can hear. So I invite the team to come over here so we can answer all the questions that we might have. Thanks so much. Let's start with the Q&A period right now. So I have the expert here that can answer the questions.
We won't have any water to use because the pit catches so much rainwater. So we won't have any external inputs. So for instance, like the processing plant, it doesn't have any water that we are taking, say, from like municipal. Okay. We will use all the water lands on site from rain, because where we live, obviously it's pouring rain today. Our water balance is actually in really good shape. We don't have to use any external water sources at all. So we'll capture all runoff of every facility we build, tailings and those types of facilities, and we'll store it and then discharge clean water, obviously. We have a discharge standard. It's the North Carolina Class C water discharge standard. And we also, during operations, we as a company want to do the IRMA standard, which is it's a mining standard, a national mining standard that is more or less, any mining division or company of reputable standing is kind of said as a unified body that we are going to go above and beyond. So, I mean, if you need to look it up, it's just IRMA water standards. So, and so it has to pass that standard, and that's what our water discharge will be, and it'll actually just flow right down Kings Creek.
The tech facility is going to be built right in the mine zone. So it's going to be an enclosed, buttressed, dry stacking tailings. So it's going to be stored at the site.
He's asking if what our waste, where our waste rock and tailings areas will be, and if that waste rock and tailings is toxic or or hazardous, so that it'll impact water quality, more or less. And the answer is no. The beauty part is that the tailings is all the white rock he showed you, right? So it's mostly, it is all literally like sand. And so when we pile that up, there's no groundwater impacts at all, no surface water impacts. Yeah, and he's actually got samples of it right here. And then our waste rock is the same. It's also really clean, and again, that's water that we will capture to use on site. So we won't have any groundwater impacts from our waste rock or tailings facilities.
So I can bring this to you, or we can talk afterwards, but it's just basically a fine powder or gravel-sized rock. And we're in the process of double-checking and characterizing, making sure that nothing crazy is leaching or anything from it. Meaning that, if it's exposed to water over longer periods of time, is anything going to come out?
Yeah.
So far, all the test work shows that nothing out of the ordinary is coming out. It's just regular stuff. And then the other thing is, you gotta remember, Kings Mountain was an operating site for 50 years, and there's waste piles all over that have been on site for 30 years, sitting down there. And there's no indication whatsoever that there is any contaminants or any dangers or hazards to the environment. But even though we have that proof, we need to, on the new material that we're in processing, we are running a whole series of tests to be comfortable to say here that we don't expect any impact based on science and the data that we have.
Yeah, precisely. We're literally doing just about 20,000 samples tests on all the rock on site that we will interact with.
So the intention is to store it across the site where we have, and Fernando just mentioned that it's a buttress facility for tailings. We're using the material that we're taking out to make sure that in the space that we have, we are controlling where it goes. But it's not, we're working through the options on where things go to try to, what do we call it, play Tetris?
That's a good term, yeah.
That's the term we're using. It's like, okay, we put it here, what is the best location? And that's not finalized yet, so to the specific, is it going to go on this particular area? We cannot tell you just yet because we haven't finalized what area or what is the best way to sequence all of that. We're still working with that.
One of the things that we said early on was that we were entering that feasibility study with the National Park Service. So that study is still ongoing. We actually added some areas to that study, so that's why it's taking a little bit longer. Essentially, the new plan that we have for the trail, we wanted to make the trail even longer than we anticipated. And so it's gonna take a little bit of time for us to get that back. But we've had a lot of positive progress already, but we're not at a point where we can announce any of that yet. But we actually, all of these meetings are ongoing with the Gateway Trail Board, with the city, with the county, and the National Park Service as well. And actually, Albemarle made the commitment to not close the old trail until the new trail is open. So we have no plans to close that trail until we've made those announcements, until we've built the new trail. And so we don't ever want there to be any interruption with the trail being of service, I guess.
I grew up in a mining camp. To me, the smell of a concentrator, for lack of better words, is happiness to me. I'm just dumb like that. But I've been in mining since I have memory. So, but particular to our case, I just came from Australia. I was there for a couple of weeks visiting our two partnerships there. And realistically, it's nowhere near what you probably have seen in Peru or Chile for copper mines. I was surprised by how little smell there is. Now,
little isn't none.
Little isn't none, but I will tell you that I was probably 150, 200 feet away from there, and you couldn't smell it. The offices were that close. And once you walk into the plant, because portions are not using these reagents, in those portions that you're not using it, inside, you couldn't tell that there was one. You had to be really, really close to the float cells, which is where you add the reagents, to smell it. But as you start walking away from it, and I'm not talking walking hundreds of yards, I'm talking walking tens of yards at most, that smell dissipates. So I don't expect it's going to be to the level that you've seen. I grew up in Peru, so
That's the smell that from a concentrator, you can smell it as you're driving to it, but you're not that close. Now, the other piece to this is that we have made we're trying to make sure that all our buildings are enclosed to minimize any potential odors outside them. So I cannot guarantee there's going to be no smell. My experience based on what I have seen is that I don't expect that to be an issue outside a very confined space around the plant. So you have the mine, and you have the waste dumps, and you have tailings, right? But where the smell comes, it comes from the reagent used within the concentrator. When I show you the flow sheet, there's a number of steps, right? On the very, not the last, the one before the last, where it says flotation, that is the step where those reagents are added.
Okay.
So if you look at, we're looking at probably 2-3 buildings. Out of those 2-3 buildings, only one is where you're gonna have it. And outside that building, into the other 2 buildings within our property, our own employees are probably not going to smell it. So if you're concerned about that, having a stinky cloud, like I drive by, on the way here, by a sewage processing place. And as you're driving by, there is a piece that you cannot avoid smelling some funny things. I don't expect we're gonna be anywhere near that. I don't expect we're gonna have that. Can I guarantee a certain stack of Bibles? I won't, because until it's built and run, every indication that I have based on the experience of what I have seen and where I have been at tells me that I don't believe that's going to be a problem. Yes, so there is a number of crushers which is no different than...
Is that going to be on site, or is it going to be someplace else?
It is going, the crushers are going to be on site. One provision we've made on the design is that all those buildings are going to be enclosed for 2 reasons. One is to minimize dust, capture any dust that there might be, and 2, to reduce or minimize the amount of noise. Now we have next to us an operating quarry that has a number of crushing stages. Unfortunately, I don't live in town to be able to tell if you can hear those crushers or not. I expect that because ours are going to be totally enclosed, the amount of noise generated from that is going to be significantly lower. 1, 2, the specific question to the grinding mill, is that going to be noisy? Yes, it gets to be noisy because you have steel balls going clunk, 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 around and around. Now, 1, the building is enclosed again. That's part of trying to reduce the noise. 2, the liners of those mills, what I found out is in our operations in Australia are rubber lines. So that helps dampen that noise versus a typical steel liner where it's a little more noise. There's more noise out of that. So we know that we're doing noise surveys around site across the board to baseline where we are, and we will understand what the impact is of, once the operation is in place. But we also have to meet all MSHA safety standards on the amount of noise that can be generated within a building. So for our own operators and employees to make sure that they are protected. So if we have to control the amount of noise within those buildings, what is call it residual noise coming out and going in outside the site it's gotta be very, very small. There is dust collection system on every one of our crushing points. You connect via conveyors in between those, primary, secondary, tertiary crusher. Those conveyors are going to be enclosed. The transfer points are going to have dust collection. So we're making every effort possible to minimize or reduce or completely avoid any dust generation across the property, not only in crushing, but in every transfer point. So he's right. We also have to meet an air quality permit where there's only so much dust that we could generate, and we're going to try our best to be well below that.
So that's a good question. Why choose the 2 mile? Why choose the 2 mile radius, right? So that was more or less, when you look at it's kind of I mean, I guess it's more of an observed parameter that we kind of use. You know, that's a good distance from a mine, or obviously in most mines, the biggest impacted area is the pit for impacting groundwater, because it's a giant hole, you know, in the ground, right? So we oftentimes just use that. That's a really common radius to use. And then we did the base, you know, that was the first study we did, was what groundwater impacts are there that are already in place, you know, first and foremost. And so that was really just determined within this, and that was like outside of thinking any kind of other characterization that had gone on. We just said, what is this radius and how many things are in there already? So it's not an expected impact zone. It's just a common used, you know, based on, you know, the history of mining and groundwater studies and things like that. We won't have any high capacity wells, because you really can't drill one. I mean, maybe high capacity to you means something different than it does to me, but we have a model that's a water balance model, and it takes into account all the weather patterns and everything historically, and then also draws data from what, you know, like universities and stuff are pulling for what they expect climate to look like, and we predict what the storms are going to look like, and we don't have a year where we won't have a surplus of water in our model. And the reason is just because that pit is such a big catcher's mitt, right? It's a giant bowl that has a catchment that's so big that, you know, a little bit of rain is a lot of water. You know, and so for instance, right now, 1 inch of rain is 1 million gallons in that pit. And so, I mean, and that 1 million gallons, that's a lot of use for us.
We are exploring all those options. We have tests were planned to look at can we make byproducts out of those, but the priority has been given for us to make sure that we have a robust flow sheet to recover lithium, and then we can start now looking at what those alternatives for those byproducts might be. Is there the option? Yes. Have we fully assessed or evaluate those? No. That's what is coming next. Yeah, I mean, chemically, yes, there is the potential, there's the possibility, it's doable. We just have to do our homework and develop those flow sheets for those specific materials, you know. But it's a work in progress, I guess.
We can also buy little crushers and the gang rock, crush it up to make a road base, keep the dust down, that stuff as well, to gravel our roads. So we'll use some of it as well for that kind of stuff.
Are we talking about the 500 acres there on 161? Mostly. Yes, just north of Lake Montonia? Yes. Right now, we have no plans, and we haven't had any plans. We don't have any future plans to use that property for any reason. It certainly won't be a part of the operation, and again, it's not planned for any reason. That's a property that we bought a few years ago, and that we've really just had, we've been holding on to, but no, it will not be a part of the operation in any way. Yes, so that is actually a part of the water study, so I'll let Joey speak to that.
Yeah, that fell within our groundwater monitoring network location. You know, we need to make sure that we have baseline information around the entire area, and baseline is so that you know what you have, so that if there's a change, you can figure out when it happened and start investigating. But so drilled some observation wells out there.
No, we're looking at a couple options, but they're all inside the property that we have now, inside the Albemarle property land that we have. So we had no plans to put facilities outside that what we already owned. With that said, and this is not only because of the commitment that we have, but also because all the facilities had to be close by because of when we move material from one side to another, it optimizes all, you know, the way that we handle the material, how we move things around. So. No, everything will be inside the property. Our current plan is for 10 years mine operation. We're looking at the reserve that we have, and we do to recent explorations. And the resources tell us that we have resource there for about 20 to 25 years. Now, everything depends on the resource based on the price of lithium. If the price of lithium gets higher, and then the resource increases. If the price of lithium decreases, and then the resource gets smaller and smaller. So everything is driven by the price and how many tons of that material can be economically mined. But so far we have seen, based on the current prices of lithium, that there is resource for 20-25 years. Currently, like I said again, we have the plan for the 10 to 12 years on mine plan. The concentrator is going to produce on a yearly basis about 350,000 tons of concentrate. And that concentrate has 6% lithium, and which is about 50,000 tons of lithium carbonate equivalent. So we're talking about moving material to the next step, which is the conversion plant at 350,000 tons per year.
Albemarle has announced that we're going to be building what is called the North America Conversion Plant, or Megaflex site, which is, the location has not been yet announced where it's going to be. It's not in Keys Mountain. It's, I don't know where the location is, but it is within a given radius from this. So our concentrate gets trained or shipped there, and that's where that conversion is going to happen. It's not going to be here. It's going to be somewhere else. And once that announcement is made, we can share where that is, but at this point, that information isn't publicly available, not even internally for most of us.
All right. We have some sample here of the concentrate, some sample of the lithium spodumene rock. We would like for you to take a look at it so you can see how it looks like. Some questions that we have about the tailing sand. I would just want to finish our presentation saying that as Albemarle, we have a high commitment to develop this mine with the highest standards, not only to operate this mine with the highest standard, but also looking at how we preserve and conserve the environment. We're looking at the latest technologies and everything that we're going to do. Now, going back to some of the questions, the reagents that we're going to be using are going to be reagents that are top-notch in terms of how friendly they are with the environment and also with people. Looking at the mitigation of noise and mitigation of dust, we're going to be having closed, concentrated, enclosed facilities. We're going to have dust suppression systems. We're going to make sure that there is no fugitives going outside the facility. And not only because we want to have a commitment with the environment, also with our people. We need to make sure that our people are working in a healthy environment and not getting any dust or anything that will cause any problem. So my commitment, our commitment is to make sure that this mine, this facility, it operates at the new generation mining that we call it, and we use the latest technology. So this is our objective, making sure that we have done a good job on the baseline, good studies. We truly understand the nature of the rock and the nature of the area. We look at the water, underground water, the groundwater, how it moves. So we really truly understand how is this mine going to operate in the future. So any other questions? If not, we can close, and we're going to be here just asking any questions that you might have that we haven't answered. So thank you very much for coming today. We will continue doing these town halls. In a few months, we're going to have the information center ready, so you can go there anytime to ask questions. We're going to have our team there once a week to answer all the questions and make sure that you get all the clarifications on all your concerns that you might have about this project. So thanks very much.